I think fundamentally, let's imagine that this is, in microcosm, a description of the air in the room. All right? So how many air molecules are there in the room? Yeah, a lot. Yeah, that's very quantitative. All right, so what do you know from chemistry?
Well, you know that there is a mole per liter.
What's the volume of the room? Okay, before, yeah, we've moved from a lot to big. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Close enough, that's halfway. 20 meters.
What?
How high is that? 10 meters. 20 meters times 10 meters times 20 more meters, but it's a triangle, so half. Okay? So the volume. Okay, now, how many molecules in what? What do you know? It's like 22.4 something or other per something or other, right? 22.4 liters per mole at STP.
Moles per liter. No. Sure. There's 1 mole per.
Are we happy with this? We are not happy. What do you want?
But moles per liter is molarity.
She wants moles per liter.
22 molar air.
I think it's liters per mole, so we'll go with that for the moment. Okay, how do I get from liters to cubic meters? How many liters in a cubic meter? 1,000. Okay, so I have 2,000 cubic meters, so I have 2 million liters, and I have 20 liters per mole. So I have N is about equal to 2 times 10 to the 6 liters divided by about 20 liters per mole. So that's 10 to the 5 moles. What's a mole?
6.02 times 10 to the 23rd.
Yeah, so this is like 6 times 10 to the 28 particles, air molecules in the room. Okay, so let's be really crude and ask, okay, what's the probability that all of the air molecules in the room are on that half of the room?
We have a vacuum across the room.
Yeah, so this side, don't tell them, but they have nothing to breathe. Okay, over here. So this side happens to have all
But there's the ether.
the air molecules. What would be the probability of that? Well, what's the probability that any given air molecule is on one side, one half versus the other half? Probably about 50%, right? Okay, so how would I get the probability that every damn one of those air molecules is on this side?
0.5 to the power of 6 times 10 to the power of 28.
1 half
To the power of 6 times 10 to the 20.
Doesn't that frighten you?
Assume independence.
Yeah, assuming independence, okay? So that's going to be a rather small number, okay? That is, you probably would have to wait a very long time for this to happen at random. What about if we put equal numbers on both sides? Would that be more probable, or is that just as good as this?
As good as it.
Careful, think carefully.
No, there's a choose factor.
There's a choose factor, right? So this is if all on one side What would it be if I put half on one side? Well, now I have to choose which half. So for each molecule, I got to pick out of all n molecules, I got to pick half of them to go this side. But once I've done that, the other half have to be on the other side. So that would be n, if n is this god-awful number here.
And choose half.
Is this familiar notation to people? Where have you seen this? Prob stats. Okay, so then no excuse. All right, so times 1/2 to the n. So let's see, that looks like n factorial over n over 2 factorial
And over 2.
squared,
Multiplied by half.
where n is this ridiculously huge number. So even though the probability of having equal numbers on either side is fantastically small, it's way more likely than having all of them on one side versus the other. So if we just imagine that all of these possibilities are equally likely, we see way more reds because there's lots more ways that we can have most of the particles with very little energy and only a few particles that have managed to steal a significant fraction of the energy. If you want to think mechanically, imagine what happens if you're one of the purples. You're going to run into somebody, and the odds are when you run into somebody that you're going to come out a loser. You're going to go down in energy. It's not impossible that you would get more, but it's way more probable that you will end up after one of those collisions at lower energy. And so if we just let all these collisions happen, we end up with a very smooth distribution that is easy to calculate in statistical mechanics. Physics 117 plug. Okay, so StatMech is just amazing because all you have to do is tally up all your ignorance. You have no idea where this particular molecule is going to be. It's equally likely to be here and there. We just add up all the possibilities, and then we know pretty much exactly what the air is going to do. But it implies as well that we can tell the difference between forward in time and backwards in time, because if I start with a goofy distribution, it's going to evolve towards one of these that looks generic, and that would be towards equilibrium. Okay, folks, have a great weekend.